Okay, so we're learning a new rule to find derivatives, and we're going to look at finding the derivative of logarithms. But before we do that, let's just review a couple of our rules of logarithms, because this is going to help us, first of all, prove some of these derivatives, and it will also help us in the future take the derivative of something that looks really complicated and ugly. We can use logarithms to make it so simple to find the derivative. But again, let's just quickly review these rules of logarithms that you got from algebra class. And so recall, if you have some log base b and you're multiplying two things together, then we can break this down as log base b of the first piece, m, plus log base b of the second piece, n, if it was log base b of m times n. If you have log base b of a quotient, m divided by n, then we can break this down to log base b of the numerator, m, minus log base b of the denominator, n. And the other one that's going to be really helpful for us is rule 3 in front of us, that log base b of m raised to some power. We can, and then in this case it's k, we can bring that power in front as a coefficient. So k times log base b of m. One other one that's going to help us prove is this rule 7. So if you have e log base b of k, same base as your log is the base of your exponential, then those simplify and cancel each other out, giving you just k. For logarithms, a couple rules had to hold true. In order for a log to exist, your base had to be greater than 0. Your base couldn't be equal to 1 for your log. And m, n, and k are all real numbers. But recall, we couldn't take a log of a negative number. That didn't exist. We couldn't take log of 0. So m and n has to be positive. Okay, so now when we're talking about domains, a lot of times you want to look at what the argument is, what we're taking the log of, and make sure that that is greater than 0. Okay, so I'm going to give you some differentiation rules. And so some rules of derivatives. We've seen that the derivative of e to the x, that's like the easiest thing to take the derivative of, is e to the x. The other three in here we haven't seen, and we're going to prove a couple of them. So the derivative of the natural log of x, this is always going to be 1 over x. Let's look at the other log. So the derivative of log base a of x, this is going to equal 1 over x, natural log of a. If our base is not e, it's not as easy. If we have base a, our a has to be greater than 0, a can't be equal to 1. So if we have an exponential piece and a is not e, then we look at a to the x, its original piece, just like e, but then times the natural log of a. Okay, so let's look at the derivative of the natural log of x. And so let's say that y is equal to the natural log of x. Maybe we should recall this. So recall the definition for logs. So if we have y equals log base b of x, we can write this in exponential form. And so we take the base of our log of the other side, y is equal to x. Okay. And so recall that the natural log is just log base e. It's just another way to write it. And so we can rewrite this y equals natural log of x. We can rewrite this in exponential form. And so our base of our log is e raised to the y power equals x.
Snowfinger, really quick, is this 3.7 still?
No, this is 3.8.
All right, cool.
And so now let's take the derivative of both sides. And so if we take the derivative of both sides, I'm just going to denote that I'm doing that. We're going to need to use our chain, sorry, not our chain rule. We're going to need to use, yeah, we are going to need to use our chain rule, but we're also going to need to use implicit differentiation, which we just talked about yesterday. So if we take the derivative of e to the y, notice that's a function of y, which is in terms of x, we need to take the, use the chain rule. And so the derivative of e to the y is just e to the y times the derivative of the outside function, which is y, which is dy dx. Equals, so the derivative of x, that's just 1. So let's solve for dy dx. And so if we solve for dy dx, we would just divide both sides by e to the y. And so dy dx is equal to 1 over y. Oops. I'm sorry, not 1 over y. I'm thinking ahead. It is equal to e to the y. Okay, let's go back and let's substitute in what y was. Recall at the beginning, y was the natural log of x. And so if we rewrite this, dy dx is equal to 1 all over e raised to the natural log of x. But one of those rules that we were just talking about, rules of logarithms, if it's the same base as our exponential piece, is the same base as our log, the natural log is log base e, then those kind of cancel out with one another. And it's the same thing as thinking of that as 1 over x. Okay. Which I just showed you was the derivative of the natural log of x. So we just showed that derivative. So I'll call that kind of square at the end is like a proof that we just showed. That's why that's our derivative and we can use it now. If it was a natural log of some function f of x where it wasn't equal to x, then we can rewrite this. So we have another rule. So if we have y is equal to the natural log of some function f of x, we're going to need to use our chain rule here. And so our outer function in this case is our natural log function. And so when we take the derivative of this, so dy dx equals 1 over what we were taking the natural log of, the inside of our function f of x, times the derivative of the inside. And so recall we can write the derivative of the inside as f prime of x. And so the derivative of the natural log of f of x is the same thing as saying the derivative of the inside all over the inside of what we were taking the natural log of. Okay, so here's another derivative rule for logs. So our stipulations still have to hold true that what we were taking the natural log of, that has to be greater than 0 because it's undefined. If it's a natural log of a negative number, x has to be greater than 0. Okay, so let's look at let's look at some examples with natural logs in there and taking derivatives. Okay, so we have two examples in front of us. We have the natural log of x quantity squared. And we have, sorry, I might have said that wrong. So we have, and the other one is y equals quantity squared, just natural log of x. Those are not the same thing. So we can use properties of logs for this first example. So if we have what we're taking the argument of that log is raised to some power, we just saw that we can bring that power down front. And so this is the same thing as y is equal to 2 times the natural log of x. And so now finding the derivative of this, well, we have our coefficient in front times the derivative of natural log of x, which is just 1 over x. So this is 2 over x. Let's look at this. Let's say you did not notice that rule of logarithms. If you didn't notice that rule of logarithms, then we're going to have to think of this as using the chain rule. So if we looked at this using the chain rule, we would have to look at the derivative of the natural log, which is 1 over what you're taking the natural log of. And in this case, it is x squared times the derivative of the inside. So the derivative of the inside, derivative of the x squared, is 2x. And so notice that simplifies. X cancels with 1 in the denominator, and so we're left with 2 over x. Same thing we got here. So our next example, y equals that quantity of the natural log of x, that quantity is squared. This again, we're going to need to use the general power rule and chain rule of the chain rule. So if we bring our power down front of the inside, which is the natural log of x, times the derivative of the inside. And so the derivative of this inside is 1 over x. So I probably just would write that as a single fraction. So same thing as 2 natural log of x all over x. I technically could bring that 2 up into the exponent there, but I don't know if that would help me with anything. So I'm just going to leave it like that. Okay, so let's look at another example. And so our next example, we have y is equal to the square root of the natural log of the square root of x. And we want to find dy dx. Okay, so let's rewrite this. We know that we can rewrite this instead of having the radicals in there, we can rewrite it as to the 1/2 power. So we have here y is equal to the natural log, well, the square root of x in there, we can write as x to the 1/2. And then that square root, main square root, we can also write as to the 1/2 power. Inside this main parentheses, we can use properties of logs to bring our exponent down. So let's rewrite this as y equals 1/2 times the natural log of x. And then this is all raised to the 1/2 power. Okay, so we're going to need to use the chain rule. So our outer function, we can think of it as u to 1/2 power. So 1/2 of the inside, subtract 1 from our exponent, so we get negative 1/2. I might leave that inside piece. Well, I guess we can, as the natural log of the square root of x in this part. But when I take the derivative of the inside, I have my 1/2. And then natural log of x, derivative of natural log of x is just 1 over x. So I have a 1/2 here times this 1/2 here. So that's going to give me 4 in the denominator. 1/4. This, I have an x from here. And then let's bring down this natural log square root of x, all raised to the negative 1/2 power to the denominator. So we'll have a square root of the natural log of the square root of x. Let me see if there's any questions. Okay, so our next example is y equals the natural log of, so parentheses, in the numerator, we have the square root. Underneath the square root, we have the sine theta times cosine theta, all over 1 plus 2 natural log of theta. And we want to find dy dx. So this looks awful. I mean, if we look at this, we're going to have to use the chain rule. When we take the derivative of this inside, we've got to use the quotient rule, we got to use the chain rule, we got to use the product rule. It just looks hideous, and I probably would make some errors as I went through and solved this, because there's so many different steps in here. But good old logs. We can use these properties of logs to rewrite this as a string of logs. So you might have remembered this from algebra, where you had this kind of messy log that you rewrote as a string of simpler logs. And so let's break this down. So notice that we have a log of division. So we're going to break down this division piece. And we know that we can write that as 2 separate logs with subtraction in between. So we're going to rewrite this. So I have the natural log of my numerator. And as we rewrite that numerator, let's rewrite it with that 1/2 power. So we have the natural log of sine theta, cosine theta, and that's all raised to that 1/2 power, minus the natural log of my numerator. So in my numerator, I have 1 plus 2 natural log of theta. So that first natural log, I can simplify. I can use the rule that I can bring my exponent down front. And so we can bring this exponent down front, and that would give us 1/2 the natural log. It's okay with you. Notice that this natural log in here, it's multiplication. We have a sine theta times cosine theta. So we can break down a natural log that has a multiplication as a natural log of the first, in our case, sine theta, plus the natural log of the second piece, which in this case is cosine theta. I'm gonna close off my bracket because that was just this natural log, but I have that 1/2 out front. I cannot, don't distribute this natural log. We can't do that. But we can rewrite this natural log of 1 plus 2 natural log of theta. Okay, so now it's in the place that we can go through and we can take the derivative. And so y prime is equal to my 1/2 out here. It's just going to stay there. So now let's look at the derivative of this natural log of sine theta.
Ms. Thompson,
Mm-hmm.
wouldn't that whole entire, all of that be multiplied by the natural log? Because you have the y equals the natural log, and then all the stuff inside is like the beginning of the problem.
Yeah, so before I'm even taking the derivative, I'm rewriting it. So remember that the derivative of division, if you have a natural log of division, we can rewrite it with subtraction in between of the numerator. And so that's
I understand that, but I was wondering about the outside, because you have the natural log times all of that. Is that just kind of, are you distributing that natural log through to those parts as you go, or?
So that's not, it's not really natural log times, because natural logs are just they're a function. And so it's natural log of this argument. So, and I'm using the rule that if you have some log of a divided by b, this is the same thing as the natural log of a minus the natural log of the denominator.
I see. Okay, thank you.
Yep. And then I was using the rule here that if we have the natural log of something raised to a power, that we can bring the power down front. And so that's where this 1/2 power came from. And then the other rule we're using that if you have natural log of multiplication, then this is the same thing as the natural log of the first piece plus the natural log of the second piece. And so now, just by rewriting it, now we're going to look at this and take the derivative of each piece. And so just really quick, because we're just learning this, if we have y equals the natural log of some function f of x, then the derivative of this is equal to, it ends up being the derivative of what we're taking the natural log of over what we were taking the natural log of. And so now when we look at the derivative of this natural log of sine theta, let's think of the derivative of the inside. Derivative of sine theta is cosine theta, all over the original function we were taking the natural log of, which is sine theta. So plus, now take the derivative of natural log of cosine theta. So derivative of the inside, derivative of cosine theta, that's negative sine theta. All over the original, which is cosine theta. So that was the derivative of the first grouping. Now looking at minus. Now looking at the derivative of the second grouping. So I'm going to have to apply the chain rules twice, it looks like, because when I take the derivative of the inside, let me think about this, maybe not. When I take the derivative of the inside, derivative of 1 is 0, plus 2, now the derivative of natural log of theta, I guess that I don't have to, this is 1 over theta, divided by what we were taking the natural log of, which was 1 plus 2 natural log of theta. I'm just curious how far we want to clean this up. Okay, so we want to clean this up some, and we know we need to use some rules of trigonometry. So remember cosine theta over sine theta, that is the same thing as cotangent theta. So we're going to rewrite this as y equals 1/2 of cotangent theta. And then we have minus sine theta over cosine theta, that's tangent theta. Minus, so we have over here a complex fraction. We have this 2 theta, technically, because 2 times 1 over theta is 2 over theta, all over 1 plus 2 natural log theta. So let's multiply top and bottom by theta. And so if we do that, in the denominator, I would have theta all times 1 plus 2 natural log theta. And in the numerator, this theta times 1 over theta, that's going to cancel, times that 2 is just 2. And that's the derivative, so I should have a y prime there. It looks like that is as far as we can take that. Unless we wanted to get a common denominator. Let me just make sure they didn't get a common denominator. No, they didn't. Okay, so here's an example where we're going to use what is called logarithmic differentiation to find the derivative. And we have y is equal to the square root. Underneath the square root, we have in the numerator x plus 1. That quantity is to the 10th power. And then in the denominator, underneath the radical, we have a quantity x plus 1. And then that whole quantity is raised to the 5th power. So here's a case where we might want to take the natural log of both sides before we take the derivative, and then let's rewrite it using properties of logs to rewrite that one side as a string of simpler logs. And so if we take the natural log of the left side of the equation, we got to take it of the right-hand side of the equation. And because I know I want to use that property to bring an exponent down, let's rewrite this radical as to the 1/2 power. And so I have the natural log of x plus 1 raised to the 10th all over 2x plus 1 raised to the 5th. So now let's use that property of log that we can bring the 1/2, the exponent, down in front. So we have the natural log of y on the left-hand side equals 1/2 now the natural log of x plus 1 to the 10th all over 2x plus 1 to the 5th.
Wait, can you just solve this without a natural log?
You could,
Okay.
but I think it's going to be so much faster if we don't, because if we solved it without the natural log, we're going to have to use, again, the chain rule. And then once we use the chain rule and take the derivative of the what's underneath the radical, the radicand, we'd have to use the quotient rule. And within the quotient rule, we're going to have to use the chain rule. So this is going to make it so much easier. And so if you have a division, when you're taking the log of division, you can look at the natural log of the numerator. So we're going to look at the natural log of x plus 1 raised to the 10th power minus the natural log of the denominator, 2x plus 1 raised to the 5th power. And so again, I can use those rules of exponents to bring these exponents down front. And so doing that, we still have the natural log of y, and that one side equals 1/2. And now we have 10 natural log of x plus 1 minus 5 natural log of 2x plus 1. So now let's go through and take the derivative of both sides. When we take the derivative of both sides, though, notice that the one side we have a natural log of y, and y is a function of x. So we're going to have to use implicit differentiation here. So I'm just rewriting this. And so when we take the derivative of the natural log of y, using differentiation, we need to use the chain rule. So the derivative of the natural log of y is 1 over y times the derivative of the inside. Well, the derivative of y is this dy dx. Equals. So I kind of not like, I really don't like that over here. So think of dy dx, that's the derivative of y. Let's just put that in the numerator. Okay. Is equal to, we still have that 1/2 out front. And now we can go through and we can take the derivative of each piece. So 10 is going to be left alone. So derivative of a natural log, look at the derivative of the inside. Well, derivative of x plus 1, that's just 1. All over the natural log of what we're taking. So all over x plus 1. Minus 5. And then we look at the derivative of the inside. Derivative of 2x plus 1 is just 2. All over what we were taking the natural log of, 2x plus 1. Okay, so we really want the derivative. We want dy dx by itself. So what we could do is we could get rid of the y on the left-hand side by multiplying both sides of our equation by y. And so our y's cancel here. And that leaves us with that dy dx, the derivative, which we were trying to find, equals, oh my goodness, let's right now keep it as y over 2. And here we have 10 all over x plus 1 minus 10 all over 2x plus 1.
Ms. Knopfseger, where did the 2 in the numerator come from in 2 over 2x plus 1?
2 in the numerator. Okay, so that was from this piece when we took the derivative. And so, or just the 5, you don't have to worry about the 5. But when we took the derivative of this natural log of 2x plus 1, we need to use the chain rule. And so we look at 1 over what you are taking the natural log of 2x plus 1 times the derivative of the inside. And the derivative of 2x plus 1 is 2.
Okay, yeah, that makes sense. All right, thanks.
Yep. Notice that we know what y is. We started with our original problem, what y was this piece in here. And so over here, we can go back in and we can replace what y is with that whole original function. Again, I'm not sure how far they're going to take it if they want us to rewrite what's inside that bracket I have as one single fraction. Notice if we distribute our 1/2 here to each term in here, so 1/2 times 10, that actually reduces down to a 5. So this would be 5 all over x plus 1. And if we distribute 1/2 over here to this minus 5 times 2 over 2x plus 1, well, the 2's would cancel. And so that would just leave us with minus 5 all over 2x plus 1. And then let's go back and replace this y right here with what our original function was, which was this square root. Underneath the radical was this x plus 1 raised to the 10th all over 2x plus 1 raised to the 5th. And this is dy dx. Okay, so there is an example where logarithmic differentiation, once you get down, taking derivative of logs, it makes your life a lot easier when you have a really difficult log to take the logarithm on both sides, use your properties of logs to rewrite it. Use implicit differentiation and then simplify.
Oh, I'm just waiting for the inverse section. It gets even funner.
Oh, you guys get to look at that tomorrow.
Oh, I love inverse. Yeah.
So the inverse function, so just let you know, you might want to review just things about inverse. So how do we find an inverse of a function? What do we know about properties of a function and its inverse? Like if xy was on a graph of one of the function, then we should know that x, swapping your x and y values, are a point on the inverse function. Recall to solve for an inverse function, you swapped your x and y values and solved for y. Had to be a one-to-one function to have an inverse. The graphs were reflections across a line, y equals x. So if you don't remember inverse functions, you might just want to go in and review that. Same thing with properties of logarithms. You can see where this is helpful.
Yes,